All right, let's go over the quiz. Screen sharing now, everybody with me? Make sure you're listening careful if you had trouble. Here, we need the chain rule, right? Because you got the 3x in there. If this were just a 4 times natural log of x, we'd get a derivative of 4 times 1 over x, or 4 over x. Here we'd get 4 times 1 over 3x, plug the inside function into the derivative, and then multiply times the derivative of the inside function. Although something interesting here happens, the 3's do end up canceling. I mean, you don't have to do this, but they do end up canceling. You get the same answer anyway. That's kind of strange. That's a power function. You get ex to the e minus 1. It's not e to the x. It's not an exponential function. It's a power function. Yeah, this does simplify to 4 over x plus ex to the e minus 1 if you want to simplify it. Why did that happen? Why did that give you the same answer as if you had an x in there instead of a 3x? Well, it's because natural log of 3x by a property of logarithms, well, that's a log of a product. That's the same as the sum of the logs, one of the things you proved on exam 1. And ln of 3 is a constant. Its derivative is 0. So the derivative of ln of 3x is the same as the derivative of ln of x, 1 over x. Kind of strange, huh? But it is true. Here we've got a quotient. We need the quotient rule. The low function is x. The high function is sine of 2x. When we differentiate the high function, we need the chain rule as well, right? Because it's sine of 2x instead of sine of x. Low, always start with the low. Always remember that. Low, low, low. Low, d high, derivative of the top. That's what I need the chain rule for. The derivative of sine of x is cosine of x. So I start to write the cosine of x. But then I remember, oh, it's not an x in there. It's a 2x. So I need to plug that in there. And then extra step, multiply times the derivative of the inside function. The derivative of 2x is 2. Low d high minus high d low. Since multiplying by 1 doesn't change anything, if you don't have the times 1 there, it's still correct. Over the square, what's below would be over x squared. Please stop me if you have any questions about these things. The way to get better at it is practice and going to math lab if necessary, finding online help if necessary, videos online or something. Getting help from a classmate, which, by the way, with your project groups, you can certainly work together on practicing for quizzes in the gateway and working on assignments. Don't copy each other, just help each other understand and then write up things on your own. This one, we've got a product, we need the product rule. Also, when we differentiate the second function, we'll need the chain rule. So we're combining rules here. F prime of x, derivative of x squared is 2x. That's the derivative of the first times the second. I put a dot in there. It's not necessary there to put a dot because it's understood it would be a multiplication. Plus the first function times the derivative of the second. Here, it is absolutely necessary to either put a dot and a -2 or put parentheses around the -2. And in fact, I'd put both. I would suggest putting both. Oops, and I made a mistake in there. 2x. Derivative of the first times the second plus the first function, x squared, times the derivative of the second one, which I need the chain rule for. I need an extra factor of -2. You all good there too? Next one. These are memorized derivatives, so if you didn't remember them, then you had trouble with this one. The derivative of tangent is secant squared. And the derivative of inverse tangent is not Well, it's not the derivative of the reciprocal of tangent. It's not the derivative of 1 divided by tangent, because that's not what this function is. That's not what this notation, the standard notation means. It means the inverse function. It means it's a function whose graph is a reflection of the graph of the tangent function over this domain. This is the tangent function right here. Reflect that across the line y equals x, and the graph of the inverse tangent looks like this. And it's got horizontal asymptotes at pi over 2 and negative pi over 2. Two distinct horizontal asymptotes. That's what the graph of the inverse tangent looks like. And that's not the same as 1 divided by the tangent function, which we standardly call the cotangent function. Standardly, is that a word? I don't know. It's a derivative to memorize. It's 1 over 1 plus x squared. A non-trig function. Interesting, but true. If this had been arctangent of x instead of inverse tangent of x, the answer would have been the same, because those are the same function. So if I put a quizzer on the gateway, you see an arctangent, it's the same as inverse tangent, the derivative is the same. Calculators tend to use this notation. Mathematica uses arctangent notation, actually. So I don't know that I've shown that to you yet. By the way, if you didn't memorize the derivative of tangent, you could have derived it from the quotient rule, because tangent is sine over cosine. If you differentiate that with the quotient rule, low d high minus high d low over the square of what's below, that is also the answer that matches secant squared. It's not obvious that those are the same, but they actually are, because the top actually simplifies to 1. You see why? Because it's really cos squared, 2 negative signs make a plus, cos squared plus sine squared x, which always equals 1, no matter what. Fundamental trigonometric identity. So you get 1 over cos squared. That's the same as 1 over cosine of x, quantity squared, which by definition is the same as secant squared. So they really are the same thing. Finally, this one can be done in a few different ways. Perhaps the easiest way is to use the chain rule. Bring the -1 down in front, plug in the inside function, subtract 1 from -1, you get -2, and then multiply times the derivative of cosine, which is negative sine of x. That simplifies to the 2 negative signs cancel, sine x over cos squared x, if you like, which also can be written as sine x over cos x times 1 over cos x, and that's the tangent function, and this is the secant function. Hey, secant times tangent. Well, this is the same as the secant function. You could have also recognized it that way and gotten the same answer. This is not the inverse cosine function. The -1 power is on the outside of the parentheses. It also can be done with the quotient. Okay. Anything I can clarify? You need to understand notation and facts. What? The derivative of arctangent doesn't have anything to do with secants and cosecants. It's this thing. Another question?
Yeah, like 4 and 5, I just write I have 1 over 1 minus x squared. That's the point off, or
I'm not sure. I'll have to look at it. All right. For the rest of the class today, I'd like to go back to the example we were looking at the end of class on Wednesday. It's a pretty fundamental example, I think, to think through again, emphasize the same things again, and maybe emphasize some new things again, including spending more time talking about multivariable calculus and something called partial derivatives. These things are not in the book, but the basics of them I want you to know for exam 2 anyway. So what you're going to learn about it, you're going to learn from me in class here, okay? Make sure you ask me if you got any questions. So this, as it stands, is a section 3.7 problem. Section 3.7 is about implicit differentiation. Yeah, that's the title of section 3.7, implicit functions. This equation defines a curve in the XY plane. Let's go ahead and do some Mathematica along the way here as we go. Probably best if you just watch me. I will email this to you after class. I think I forgot to do it on Wednesday, but I will make sure I do today's. Okay, so I'm going to plug in this function into Mathematica, and I'm actually, I should say, equation into a function called ContourPlot. Now, technically, that equation is something you could solve for y as a function of x, because you could get 0 on one side, and you could use the quadratic formula to get y in terms of x, because it only involves a y squared. It's the highest power of y. You could not solve it for x in terms of y, because there's an x cubed, or at least you can't do it very easily. The formula would be very messy. But the point of implicit differentiation is you don't actually have to solve for y as a function of x. And you can still find this derivative. You can still find the slope of the tangent line at the given point. Though, as I emphasized on Wednesday, we really should confirm that this point does satisfy the equation. An arbitrary point won't. This point does. You can check it. If you plug x equals 1 and y equals 2 into the left-hand side of the equation, you get 1 cubed, x is 1, plus 5 times 1 squared, again, x is 1, y is 2 times 2, plus 2 times y squared. This simplifies to 1 plus 10 plus 8 is 19. And the right-hand side, 4y plus 11, when you replace y with 2, also simplifies to 19. Because those simplify to the same number, that means this point is on the graph of that equation. ContourPlot can plot it, even without solving for y as a function of x. Type the equation in, x cubed plus 5x squared. Put a times in there. It's a good habit to do that. Times y plus 2y squared. When you solve equations in Mathematica, I think I mentioned this before, you need double equal signs. Now, ContourPlot isn't literally solving this equation in the usual sense, but internally it is doing some solving. So you actually need double equal signs. If you put single equal signs, it'll mess it up. Don't put the single equal signs. 4y plus 11. Put a comma. And let's do our window x going from -3 to 3 and y going from -3 to 3. This is actually a little different syntax than what I showed you in class on Wednesday. On Wednesday, I defined a function of 2 variables after subtracting 4y and subtracting 11 from both sides. I'm still going to do that here today, but I wanted to do this first. In class on Wednesday, when I did that, I got a bunch of curves, right? You remember that? Bunch of curves, shaded differently. Here, I'm only going to get one curve. There it is. But it's in 2 pieces. That shouldn't be surprising that it's in 2 pieces, because if you solve for y as a function of x with the quadratic formula, it's got a plus or minus in it. Let me make the window a bit bigger, actually. It would have a plus or minus in it, and therefore you get 2 different functions when you solve for y as a function of x. There's 2 separate functions. This is not one function. This is 2 separate functions, right? Because if you thought of these graphs together, it would fail the vertical line test. There are vertical lines that go through them more than once. Let's put the axes in there, and I think I want to get rid of the frame too. Frame, arrow, false, axes, arrow, true. There we go. Let me add a little bit more to this. Let me add the point in question. What point? The point 1, 2. How? Well, I could just imagine it right there, it looks like. But I can also get Mathematica to show it to me. I want to combine this graph with another graph. I need to put it inside something called show. I'm nesting different functions. ContourPlot is, it's kind of like function composition. ContourPlot is the inside function, show is the outside function. Although it's actually going to have another thing in here. Probably the simplest thing to do is what's called list plot, capital L, capital P. And notice the ContourPlot is a capital C and a capital P. The capitalization is essential. And inside double curly braces, I'm going to put 1, 2. There it is. There's my point 1, 2, and you can see it's on the curve. We've confirmed that that point visually, we've confirmed that it is on the curve. We want to now find the slope of the curve at that point. It's on the top curve, not the bottom one. That's fine. We want to find dy dx at that point. So how do we do that? We want to find the slope of the curve there. We use that implicit differentiation. Last time I showed you how to think of it in the standard kind of way, and I hinted at a non-standard way that maybe is a little bit easier. Today, let me first show it to you in the non-standard way. That technically is a little easier, I think, to think about, but it is non-standard. Remember, I'm assuming y is a function of x. Assume y is a function of x. That's an assumption I'm making, and now I'm going to pretend I've got a formula for it. Say y equals f of x. Is it possible to find a formula? Yes, it is. I'm just not doing it. I'm just calling it f of x. Well, if I can solve for it, why not solve for it? Well, because it is kind of complicated for one thing. And for another thing, if it were a y cubed in there instead of a y squared, then we could not use the quadratic formula to try to solve for y as a function of x. If it were y to the 5th, 6th power, 7th power, it'd be even crazier. You could not even do it at all. But the function would exist. That's the amazing thing about it. As long as you pick the point correctly, this same point wouldn't necessarily be on the same curve, on the given curve. So each y is going to get replaced by an f of x here. All I'm doing is replacing each occurrence of y by an f of x. You see how those match? There's a y there, replace it with an f of x. There's a y there, replace it with an f of x. There's a y there, replace it with an f of x. If you do this now, you see, hey, everything does depend on x. I can now differentiate both sides with respect to x. Apply the ddx operator, meaning differentiate both sides. We are making some assumptions here. In doing so, we're assuming f of x exists. We're also really assuming the derivative exists. We're assuming it's differentiable. Are those valid assumptions? That's a good question. Turns out they are, though not always, and we'll address that here in a few minutes. Derivative of x cubed is 3x squared. Derivative of 5x squared times f of x, that's a product. I need the product rule. First function, second function. Derivative of the first, 5x squared, is 10x times the second function plus the first function times the derivative of the second, f of x. What's its derivative? I don't know. I'll just call it f prime of x. I don't know what it equals, but I'm pretending I know it exists. And then with this one, I need the chain rule because I've got f of x quantity squared, and the 2 in front just goes along for the ride. With f of x quantity squared, f of x is the inside function, the squaring function is the outside function. The chain rule says, take the derivative of the outside, the squaring function, so I got to bring down the 2 in front. Multiply by 2, I'll get 4. Subtract 1 from the exponent, so I'd have f of x to the first power, which I'll go ahead and write, but you wouldn't have to because it's to the first power, times the derivative of the inside function. Well, that's just f prime of x. Got to do it to the right-hand side as well. Differentiate 4 times f of x, I'm going to get 4 times f prime of x. Differentiate 11, I get 0. What's the goal? The goal is to find the derivative. Solve for f prime. And that's what I have to do. I need to algebraically solve for it. I see an f prime here, I see it here, and I see it there. Bring all the terms involving f prime to the left side and factor out the f prime, and you'll get this. Right? 5x squared comes from this term. The plus 4f of x comes from this term. The minus 4 comes from this term after I've subtracted it. Everything that doesn't involve an f prime, these two things, put on the other side. Subtract 3x squared from both sides and subtract 10x f of x from both sides. Now divide both sides by this thing, and you've got f prime isolated. F prime of x would then equal negative 3x squared minus 10x f of x all over 5x squared plus 4f of x minus 4. On Wednesday, we wrote this as negative 3x squared minus 10x y over 5x squared plus 4y minus 4. Hopefully I haven't made a mistake. Does that look good? Let me double check that that's the same thing I got on Wednesday. Yep, that's the same thing. We're not done because we want to find the derivative at this point when x is 1. F prime of 1 would be plug number 1 in for x, negative 3 times 1 squared minus 10 times 1 times f of 1 over 5 times 1 squared plus 4 times f of 1 minus 4. But what is f of 1? What's f of 1? 2, yeah. See, look at this picture. When x is 1, y is 2. That's a 2, and this is a 2. And so we get negative 3 minus, excuse me, yeah, that's not a minus sign there. Negative 3 minus 20 is negative 23 over 5 plus 16 is 21 minus 4 is, no, 5 plus 8, excuse me. 5 plus 8 is 13 minus 4 is 9. Yeah, negative 23 ninths. And again, since that is the answer, negative 23 ninths. Since the graph of the tangent line goes through the point 1, 2, the equation of the tangent line could be written y minus 2 equals negative 23 ninths times x minus 1. I could solve that for y as 2 minus 23 ninths times x minus 1. If I want to write that in slope-intercept form, that's fine as well. Negative 23 ninths x. And then we'd have 2 plus 23 ninths, which is 18 ninths plus 23 ninths is what, 41 ninths? That would be the slope-intercept form of the equation of the tangent line. Let's add it to this graph and see that it looks right. How? keep it inside the show here. I can, maybe right there, I can put a plot. Plot plots regular functions. We've seen that before. I added a comma in there and I started to type here. Plot this function, negative 23x over 9 plus 41 over 9. X going between negative 5 and 5, though I could use a smaller window. There we have it. There's the tangent line. Looks about right, doesn't it? In fact, it is exactly right. That is the tangent line at that point. Can I clarify anything here? Do you need to know this Mathematica code? Well, I'm not going to test you on it. You're using Mathematica for the project. Watching those videos that I made is really essential for the project. People have a pretty tough time with the project if they don't watch the videos. Okay. And remember to watch them ideally together, even if you have to do it distance, and discuss them as you start working on the problems on the project. People do have a hard time with this project unless they watch the videos. Question?
Does the show function in Mathematica, is that just a way to make multiple plots on one graph?
Yep, exactly. It combines graphs in the same picture.
When will the project be due?
Okay. Now, in doing this problem, we had to know that the point 1, 2 was on the graph. And that's not obvious just looking at the equation. The book told you it was on the graph, but you can certainly check it's on the graph. What other points in this graph are on this graph? Well, again, I could solve for f of x if I wanted to. I also could try to approximate points in this graph using the tangent line as a tangent line approximation to the graph when x is close to 1, but not equal to 1. For example, if x is, say, 1.1, f of 1.1 would be approximately, but not exactly, negative 23/9 times 1.1 plus 41/9. Actually, it's even better to plug it into into this one. F of 1.1 is approximately, if I plug it into this one, 2 minus 23/9 times 1.1 minus 1, which is 0.1. 23/9 is 2 and 5/9. This is 2.5 repeating. So I can even almost do this completely by hand here. We really have 2 minus, if I multiply that point by 0.1, I need to move the decimal to the left one spot. 2 minus 0.25 repeating. And that would be, what, 1.74 repeating, I think? About 1.74. When x is 1.1, y is very close to 1.74. 1.1, 1.74, it'd be a point really close to where my cursor is right now. The tangent line and the curve are very close together. Okay. That's important to know. We're going to use linear approximations a lot, including next week. It's on exam 2. You need to know how to do this kind of thing. We can also use this derivative here, even though we haven't solved for f of x, to figure out where tangent lines are horizontal and vertical. I would like to do that hopefully before 1:40 today in the next 20 minutes. But before we do that, let's talk multivariable calculus. Let's just do it with Mathematica here. What did I do again on Wednesday? I took this equation and instead of thinking of it as an equation like this, I subtracted 4y and subtracted 11 for both sides. And I effectively, that's equivalent to saying it equals 0, that original equation. It's the same as that. And then I thought of this as a function of two variables. That's what multivariable calculus in part is about, functions of more than one independent variable. It's also about vectors and functions where the output is higher dimensional as well. The output of this function is a number, but the input is, in a sense, a point, a two-dimensional point. I can enter that function and I can plug in any point I want, like, hey, how about 1, 2? X is 1, Y is 2. The answer should be 0, right? Because that was what that curve was, where that was 0. But I could also plug in other points. How about if X is 2 and Y is -3? The output's -33. You could check it. Replace X with 2 and Y with -3. Simplify, you should get -33. There's plenty of other points I could figure out. What's f of -5, -7, -885? You could check that. So for each two-dimensional input, I get a number. X, Y, you could think of as a point in the plane. For each such two-dimensional input, I get a single number out. When you make a contour plot of this thing, let me just copy and paste this here. But let's see. Okay, I think I will keep this stuff in here. But let me change this to an f of xy. And notice I'm just typing f of xy, the function, with no double equal signs, not even a double equal signs equals 0. Now we're going to get a picture more like we saw on Wednesday. We don't get just one curve, we get a bunch of curves. Though it did happen to, it seems just by chance perhaps, draw exactly the one we had before. I wasn't expecting that. Yeah, this one is where the function does equal 0. On Wednesday, I did something else to this that added more curves, and that one was no longer in there. So let's keep it like this. For each one of these curves, along each one of these curves, the function is constant. They're called level curves. You ever seen maps of two-dimensional maps showing you elevations, like of mountains? And you maybe get a bunch of curves like this? That's analogous to what we see here. Along each one of these curves, you have different outputs. Along this curve, the output is 100. Along this curve, the output is 200. Along this curve, the output is 300. Hey, it's getting lighter up this way. Lighter corresponds to higher outputs. Along this curve, it's -100. Along this one, it's -200. Hopefully the internet's not lagging. How's your Wi-Fi? Not moving too fast? Okay. This one, it's -300, -400. Right, well, it's not showing it. The outputs are becoming negative. It gets darker. The shading indicates how high the output is. Lighter shading means higher output. Darker shading means lower output. This is not the only way to plot this function. You can use something called Plot3D. Let me just copy and paste this part here. Guess I don't have to because it's not too much to type. To plot a three-dimensional picture of this function. What in the world is this showing us? It is the graph of this function in three-dimensional space. Then I can twirl this around if I like as well. Where are the x and y axes in this picture? Listen carefully. I'll tell you here. The origin's in the middle, pretty much, yeah, right smack dab in the middle of the box. The positive x-axis goes to the right and exits the box in the middle of this rectangle on the right side. That's the positive x-axis. The positive y-axis goes this way toward the back of the box and exits through the middle of the back rectangle. There's a third axis, a z-axis, going straight up and down. And the positive z-axis goes through the middle of the top of the box. A third dimension. Z representing the outputs of this function. for each point in the plane, the XY plane, which would be about like I'm tracing here, would be the XY plane, a plane slicing through the middle of the box, and you need to imagine it horizontally if you're thinking with perspective, like you're looking down on this box. For each point in that plane, the point on the surface that you plot has coordinates that are the same XY coordinates that you started with, and then a third Z coordinate that is the output of the function. And notice the outputs are high up here and over here, just like this shading is light over here and over here. And the outputs are low here and here, just like the shading here is dark here and here. In fact, to make these level curves from this plot, you would slice this plot with some horizontal planes. And where the horizontal planes intersect this graph, you would see these curves. In fact, let me even do one here. Let me put this inside a show. Actually, I don't even have to do that. I could keep it just the Plot3D, but let me put this inside curly braces and add a, say, comma 100 in there. That'll plot also a plane whose Z coordinate is 100. All right, get rid of that comma at least. There it is. It's slicing the original graph along a curve here and along a curve over here. Those curves that you see exactly match this curve here and this curve here. These curves are in fact above those curves. You'd have to push them down to the XY plane to see it. If I do this, it makes it a little bit see-through here. Yeah. If you push these curves of intersection down to the XY plane, move them down by 100 units to Z equals 0, which is below it here, those curves would match these curves here and here. Can we differentiate functions of two variables? Sure. And when we do, we call such derivatives partial derivatives, because the function is being, you might say, partially differentiated, not fully differentiated. So coming back to thinking about this by hand, I was what I'm going to do now. Well, maybe I shouldn't call the function f since I already used f. Well, let me change the name of the function to say g here. It's not the same function as I had on paper here. Let me change all the f's to g's. It's not changing anything because it's just a label. Okay, so now I'm going to let, so what I did here is I let g of x essentially be this thing minus 4y minus 11. Go ahead and write that by hand here. G of xy equals x cubed plus 5x squared y plus 2y squared minus 4y minus 11. And when g of xy equals 0, that corresponds to the same equation from the previous piece of paper. If it equals something other than 0, then it's a different equation, a different curve. I can differentiate this. Let's call the output z. Mathematicians tend to put lines through their z's because otherwise it looks too much like a 2 sometimes. How? I can differentiate this. Well, I could differentiate z with respect to x. Question?
2y to z or 2y to 2?
That's 2y squared. That's a 2 here. If I don't have a line through it, it's 2. Actually, when I was really young, I used to make my 2's fancy like that, but then it looks too much like a Q, a capital Q. So, okay. Anyway, I also get a little lazy, even though that's prettier. But differentiate this with respect to x, for example. I could pretend the y is a constant when I do so. But wait a minute, isn't y a variable? How can you pretend it's constant? Because I want to, that's why. Really, is that allowed? Sure it is. Whether a symbol, a letter is a variable or a constant or a parameter, it's all in your mind. It's all in how you're thinking about it. This is a big point of emphasis that I make a lot. And the right way of thinking about it makes all the difference in how you think about analyzing it, you might say, and applying it. I could pretend y is a constant here and differentiate this with respect to x. I could find dz dx. Okay, I'm going to write dz dx, except my d's are going to be fancy looking. dz dx, except my d's are weird d's. They're not really d's in the usual sense. But we still sometimes say d. When you see sort of a weird looking d like that, well, you can say d, even though it doesn't look like a d exactly. Or sometimes people say partial z, partial x instead of dz dx. But I'm okay just saying dz dx. But we make them funny looking to remind ourselves that z depends on more than one variable. And when we find dz dx, we're just pretending the other variables are constant. In this case, it's just one other variable, y. So just differentiate this as if the y is a constant. This is different than the implicit differentiation. With the implicit differentiation, we made the assumption that y depended on x. Now we're pretending y is constant. Again, it seems weird, like, how can you do that? You can. It's all in your perspective. So the derivative with respect to x is 3x squared plus, differentiate this with respect to x, treat the y as a constant. Just keep it there. Bring the 2 down in front to get 10x to the first power times y. You don't need to use the product rule like we did when we did implicit differentiation, because we're pretending y is constant, not a function of x. It's weird, but you just got to get used to it. That's the way to think about it. And I'm telling you stuff that is the accurate way to think about it. You have a question? Well, if it's a constant, it's like a 7, say, pretend. Then it just stays there. That's the linearity property. Yeah, but I'm not going to differentiate it, and I'm not going to use the chain rule. Yeah. Okay. I'm not going to use the product rule. You actually could use the product rule and get, okay, 10xy plus 5x squared times the derivative of y with respect to x, which would be 0 if y is constant. You could do that, but it's more trouble than it's worth. Hey, that's a constant, 0. There's a constant, 0. There's a constant, 0. The answer is just this. If you pretend y is a constant, which you do with partial derivatives. If I differentiate with respect to y, I treat the x as a constant. Derivative of x cubed with respect to y, if x is constant, is 0. Differentiate this with respect to y, treat the 5x squared like a constant, like a 10 or something. It just stays there. But then the derivative of y is 1, so I get 5x squared times 1, which I won't bother writing. Differentiate that with respect to y, I'm treating the x as a constant now, and y as a variable, I get 4y. Differentiate that with respect to y, I get -4 and then plus 0, or -0 if you prefer. So this is the answer for the partial derivative with respect to y. What does this mean? Is it useful? Those are all questions we'll look at on Monday. For the rest of the day today, let me keep going and show you you can compute second order partials, second derivative, so to speak. I could do a second derivative of z with respect to x twice. I could write this kind of thing in the Leibniz notation. Once again, treat y as constant. I get 6x. Differentiating that with respect to x. Differentiate this with respect to x, treat y as constant, I get plus 10y. Okay, so I did it. Fun, fun. I could also do this part, second partial derivative. Once again, go here, now treat x as constant. Get 0 plus 4 plus 0 when I differentiate with respect to y. I just get a 4. I wonder if I could also, in looking at this thing, which I got by pretending y is a constant, change my perspective and pretend x is a constant. And find the derivative of that with respect to y. And the answer is, of course you can do that. You can change your perspective in such a way. Is this a second derivative? And we often write it like this, without parentheses. It's called a mixed second order partial. I first differentiated with respect to x to get this one. And then I'm differentiating with respect to y to get what? Pretend x is constant now. Derivative of that is 0 now, and the derivative of this with respect to y is 10x, if x is constant. And I could do a similar kind of thing with this one. I could differentiate that with respect to x, pretending the y is constant. Look at that again. Pretend the y is constant. X is the variable. I get 10x. Hey, those match. Even though I got them in different ways. Oh, by the way, the shorthand notation for this without parentheses would be this. Those match. Was that an accident? No. That'll always happen as long as your function is sufficiently nice, which we only deal with sufficiently nice ones in here. It's called Clairaut's theorem. Clairaut, I might be spelling this wrong. Clairaut's theorem guarantees that even though we got those answers in different ways, they will match as long as your original function is a nice function, like its second order partial derivatives exist, and actually they're also continuous functions. It's not an accident. Okay, so no applications at the moment. I do want to hint at some applications next week, and also how to interpret these things geometrically. I think it is worthwhile to put this in Calc 1. You'll see if you take Calc 2, some of this in Calc 2 as well, most likely. And if you take multivariable calculus, you'll definitely see it. It's worthwhile because it's got important applications. Okay, I think it is worthwhile for people in Calculus 1 to see the basics. Of course, in multivariable calculus, you go into much more depth than we're going to do. Like, why does this stuff work, for one thing, and much more applications than we're going to talk about. You can still, I'll give you a hint, you can still interpret these things as rates of change. Okay? Just like regular first derivatives from Calc 1, single variable calculus. All right, have a good weekend.